Dmitry, you're welcome, please.
Okay, thank you for introduction. My talk is about one approach of SAT solving, not very popular approach, but the goal of my talk, I want to explain you why it might be interesting, maybe perspective. I'm sorry, this talk will be too theoretical because I'm not expert in SAT solving. I understand something about pro systems, but to understand this talk, it is not necessary that you follow the previous talk. I will define all notions again. Okay, my talk is about ordered binary decision diagrams. What is ordered binary decision diagrams? This is a way of representing of Boolean function. Boolean function represented by a graph, by direct acyclic graph with one source node and two sinks node. And one sink node is labeled with 0 and one with 1. Every other node of this graph is labeled by a variable, and it has two outgoing edges. One is labeled by 0 and one is labeled by 1. And if you want to compute a function, you start in the source node and go along edges corresponding to value of corresponding variables. And this path will finish in a sink node, and the sink node is labeled with the value of the function. And OBDD has the following following restriction. In all paths from the source to a sink, variables appear in the same order. And it is important, and I will explain why. First of all, let's note that order of variables is important. Consider, for example, a very simple Boolean function equality. It has 2n Boolean arguments, and equality of x and y equals 1 if and only if the strings x and y are equal. First of all, consider order when variables x1, y1, x2, y2, and so on, xn, yn. And it's easy to see that there is short OBDD representing this function in this order the first picture shows. And if we consider order, then variables x precede variables y, then OBDD requires exponential size. And it's easy to see because when we read all x's, we should save their values because we not read y's. And when we read all x's, we should get 2 to the n different nodes. Okay, and some more examples for important function for us. First of all, parity function. Parity is represented by OBDD, short OBDD, in any order. And the idea is on the picture, on the left-hand side, we compute partial parities, first x1, x1 plus x2, and so on. And in the left-hand side, in the left part, the current parity is 0, and in the right-hand side, the current parity is 1. The next example is very easy, is a just large disjunction. It also has very short and easy representation as OBDD. And this example can be extended by arbitrary clause. If we also have negation here, we also know it is modified by easily way, some zeros and ones flipped. And the third example is linear threshold function. Namely, we have inequality with integer coefficients and Boolean variables. No, and the function is true if this inequality is true and false if not. If all coefficients are small, then this function also has short representation as OBDDs. The idea, we compute the partial sums, and for example, if partial sums is s, and we split it by variable xi, when for the value 0, the partial sum is also s, and for value I, the partial sum is increased by AI. And on the bottom level, all partial sums that less than B, we unify to the 0 things, and that at least B, we unify to 1 things. Okay. I said that the restriction that on all paths we have variables in the same order are very important, but no, it's very large restriction. But using it, we can manipulate with OBDDs very efficiently. First of all, if we have a Boolean function represented in OBDD, it's very easy to verify whether it's stable or not. Just we verify that there is a path from the source to one thing. Second, it's very easy to compute negation of the function. We just flip 0 and 1 things. It's also rather easy to compute any Boolean operation of two functions. The complexity of this is a product of the size of two OBDDs. It's extremely easy to apply restriction to a function. And why many people like OBDDs? Because of the next property that given the order, there is a very fast algorithm that constructs the minimal size OBDD for this order of variables. There are also efficient algorithms that given OBDD in one order that construct OBDD in another order, and the complexity of this algorithm is polynomial in sizes of input and output. But manipulating with OBDDs with different orders usually very hard. For example, if we just need to verify that function D3 is conjunction of D1 and D2, where this OBDDs uses at least two orders, is NP hard. Okay. In the next of this talk, first of all, I will talk about proof systems based on OBDDs. And after it, I explain some of approach to solving that are connected with these proof systems. First of all, I very briefly remind what we understand by proof system. Consider we have a Boolean formula phi in conjunctive number form, and the goal of proof system is to show that this formula is unsatisfiable. I briefly remind two proof systems, two classical proof systems. First of all, the resolution. In resolution, proof lines are clauses. We use clauses of initial formula, and we can infer new clauses using the only one rule, very simple rule. And the goal is to infer an empty clause that is a contradiction. And if you want to prove that formula is unsatisfiable, you use this rule and derive new clause. And if you derived the empty clause, you prove that the formula is unsatisfiable. Okay. The resolution proof system is in the base of CDCL algorithms. If we run CDCL algorithm on unsatisfiable formula, then in some sense produce resolution proofs. There are hard formulas for resolution, but hard formulas, I mean the formulas that requires extremely large proofs in this proof system. And as Edward already said, that hard formulas, pigeonhole principle, and SAT formulas that are actually linear system over F2. But you probably understand that linear systems are easier, that they can be solved by Gaussian elimination, for example, but they are hard for resolution. And it means that these formulas should be hard for CDCL algorithm because they produce resolution proof, and this proof is very large. Okay, the next proof system classical proof system I already want to discuss is the cutting planes. In this proof system, the proof lines are inequalities with integer coefficients, linear inequalities with integer coefficient Boolean variables. The particular set of rules is not so important for him, but we represent clauses of initial formula by inequalities, and we derive new clauses using some sound rules. And the goal is to derive a contradiction. In this case, contradiction is 0 is at least 1. And cutting planes are in the base of pseudo-Boolean solvers. And the formulas that are hard for resolution I mentioned here are more or less easy for cutting planes. Pigeonhole principle is easy. Linear systems are at least quasi-polynomial. There is quasi-polynomial proofs for linear system in cutting planes. This is a rather recent result. But there are also known hard formulas. Clique coloring principle that says that it is impossible that graph has clique of size k and simultaneously colorable in k-1 hence. And also a rather recent result that binary pigeonhole principle is another representation of the same principle. No, it's not very important for us. And also it's important that cutting planes simulates resolution. And even cutting planes with small coefficients simulate resolution, then we're not allowed to have very large coefficients. And cutting planes is also strictly stronger than resolution. Okay. Now I will define OBDD proof systems. In OBDD proof system, proof lines are represented by OBDDs. We have a formula phi. That's the conjunction of clauses. We choose some order of variables, and every clause of this formula we represent by p-ordered BDD. And we have some set of rules that allows us to derive new OBDDs. Okay, let's consider. First rule, every OBDD proof system has these rules. It's just a conjunction rule. We have two OBDDs, D1 and D2, and we derive the OBDD for their conjunction. The second rule is very strong rule. For resolution, it was not so strong, but for OBDDs is very strong. It's weakening rule. We have OBDD D, and we know that OBDD D1 is semantically implied by D. And then we can to derive this. The next rule, projection rule, we have OBDD D and some variable x. We can derive the OBDD for function exists x d. And it's easy to see that projection rule is a partial case of weakening rule. And usually when we consider different proof system, we do not include both of these rule because since the projection is partial case. But projection has very good property that there are not too many projections. There are a lot of possible ways how to apply weakening rule, even infinitely many. But we have only n, if we have n variables, many ways how to apply projection rule. And also one additional reordering rule when we just change the order of variables in OBDD without changing the Boolean function. But I want to stress that in conjunction rule, it is important then we apply it for two OBDDs in the same order. In other case, it would be very hard, NP hard to verify the correction of application of this rule. And the goals to derive from the initial OBDDs, OBDD representing constant false function. Now I defined actually not one proof system, but many proof systems, and every such proof system defined by the particular sets of rules. For example, we can include only conjunction rule, we can include only conjunction weakening, only conjunction reordering, and so on. And now I will speak about this proof system, some of this proof system in details. Okay, first of all, let's consider a very simple proof system that consists of only one conjunction rule. This is not too powerful for proof system, but it's rather reasonable. For example, it has short proofs for unsatisfiable 2CNFs, for formulas that are solvable but by unit close propagation, and so on. Several years ago, we proved that even if we add to this proof system reordering rule, then pigeonhole principle and setting formulas are hard for this proof system. However, resolution and cutting planes do not simulate OBDD with just conjunction rule. But separation today is not exponential, but quasi-polynomial. Also, it is known in other case, if we have conjunction and reordering rule, then this proof system does not simulate even tree-like resolution. There exists a formula that has polynomial refutation in OBDD and only quasi-polynomial in resolution in cutting-planes. And open question for this proof system is the complexity of random 3CNF formulas. We don't know. No, we suspect that they should be hard, but we don't know how to prove it.
Am I right that simulate means that system is more strong?
When I say simulate, it is not more strong. That the proof system pi1 simulate pi2 if for proof in pi2 we can construct proof in pi1 that is not significantly larger.
Okay, isn't it the same with stronger?
It's different.
At least as strong as this proof system.
Okay, in a few slides, I will give you the whole picture, the full picture, what we know, and I think it will be clear for you. Okay, the next proof system I want to discuss, if we enter the projection rule. This proof system was defined by Tserias, Kalaitis, and Vardi, and in this proof system has short proofs of unsatisfiable linear systems. This is because well, first of all, we already know that OBDDs has short representation of parities. If we have a linear system over F2, then every equation is a parity or negation of parity.
Sorry, question, what is F2?
F2 is a field of two elements, or calculation modulo 2.
Like 0, 1.
0, 1.
Mm-hmm.
Thank you for question. Okay, and it is known that by Gaussian elimination to refute a linear system is possible just to adding several equations. And here we can add equation if they have shared variables. And this is because we have, for example, two equations, we compute a conjunction of them, and after it we apply projection operation on the common variable x, and it's easy to verify that the result is just the sum of these equations. There are also known short proof of pigeonhole principle. This proof system simulates and strictly stronger than resolution. Why simulates? Because using projection rule, we can simulate this resolution rule. We have two clauses with x with different signs. We take a conjunction of them, and when we take a projection on x, we exactly get the result of resolution rule. And why it's a strictly stronger? Because pigeonhole principle and unsatisfiable linear system are hard for resolution. It is open whether this proof system can simulate cutting planes. I put this star because I mean cutting planes with small coefficients, because if we have small coefficient, that linear inequality can be represented as a small OBDDs. It is
small means 0, 1?
Small bounded by some polynomial in number of variables. Okay, and the next proof system is OBDD and weakening. And as I already said, projection rule is a partial case of weakening, because hence this proof system simulates the previous one. And for this proof system is known that it simulates cutting planes with small coefficients. The reason of this is rather trivial, because we can represent any linear inequality by small OBDDs, and all rules are sound. That's why they may be simulated by conjunction weakening rule. We just make conjunction of two inequalities, and by weakening we derive the result of rule. Also, we proved that this proof system has short proofs of click coloring technologies, and it means that this proof is stringly stronger than cutting planes with small coefficients. However, this proof system is rather strong from my opinion. However, we know lower bound for it. It was proved by Krajcik. Some exponential lower bound for some set of tautologies that are not easy to describe. And the open question is if there is a difference between projection and weakening rule, can the proof system with projection rule simulate proof system with weakening rule? Okay. We also have the result that reordering rule always makes proof system stronger. If we have proof system without reordering rule and we add it, that the result in proof system becomes strictly stronger. And now I am ready to show you the whole picture. This is the state of the art of all mentioned proof system about simulations. For example, solid lines means that the proof system, one proof system simulate other proof system. But usually all solid lines are trivial. But if from one proof system there are no paths to other proof system, it means that this proof system does not simulate this proof system. We have some separation. But dotted line said that simulation is open. For example, if we have only dotted line path, it means that we don't know currently if there is a simulation or not. Okay. This is more or less all that I want to say about proof systems based on OBDDs. And now I want to describe one possible approach for SAT solving using OBDDs. I not mentioned that we don't have proof lower bounds for these two proof systems. For all others, we know lower bounds. And there is another there is a problem.
Sorry, and they're exponential, of course.
Yes, exponential lower bounds. If reordering rule, if we add it for rather strong proof system, then all proof complexities methods breaks. That only for very simple proof, only if we have conjunction and reordering, then we can prove. But there is some principal problem that reordering rule prevent of ruling lower bound, no, according to for the current methods. Okay, and now I will discuss OBDD-based algorithm for SAT. What is the difference between algorithms and proof system? Proof system works only for unsatisfiable formulas, and algorithms can be applied for both unsatisfiable and satisfiable. But if we want to solve both of them, then we have some restrictions. Consider the following algorithm. We choose some order of variables and create OBDD that use some particular order pi. And let S be a set of clauses of phi. And until the set S is not empty, we apply one of the following operation. And we have three types of operation. First type of operation is conjunction. We choose a clause from S, delete it from S, and add it to D. That means that we change D by conjunction of D and C. The next rule is, next operation is a projection operation. If for some variable X, all clauses that contains X are already downloaded to D, that X doesn't appear in S, then we can apply this projection to D. This requirement that X is not appear in S is very important, because otherwise we can lose satisfiable assignments. And also reordering rule that in some sense we may decide that we want to change order in our diagram D. And in the end, if all clauses are downloaded, we just report whether D satisfiable or not. This algorithm answers only on the question if the formula is satisfiable or not, but it's also easy to restore satisfiable assignment if we save the values of these when we apply projection function. If we have a satisfying assignment after projection, that's very easy to find before projection. Just apply the values of variables to that OBDD, and we will get OBDD with only one variable, and it's easy to find its correct value. Okay, running time of such algorithms polynomially connected with the size of largest representation of D. And also maybe this algorithm depends on heuristic, how to choose clauses, how to choose what operations we should. No, I ignore that. This also may take time. In 90s, this approach was used that used only on a conjunction rule, and it has trivial problems that there are a lot of CNF formulas, satisfiable CNF formulas that have no short OBDD representation. That's why if you download all clauses, you necessarily will get very large OBDD. They require a lot of time and a lot of space. Aguirre, Vardy, and Panin-Vardy exploit the approach. Then they use conjunction rule and projection rule. Okay, and they call this approach as symbolic quantifier elimination. And first of all, when we apply projection rule, it's actually what we restrict x with 1 or restrict x with 0. And the size may be, is at most quadratic of the size of previous but usually in many cases the size is not increased significantly. For such algorithm, for example, SAT formulas are easy, and SAT formulas can be solved very fast by very easy heuristic when you just take a variable and download all clauses with this variable, apply projection, and repeat it until you download all clauses. For pigeonhole principle are also easy, but for pigeonhole principle, it's very important to take very clever order variables. I want to motivate this example motivate that it may be if you start with the wrong order of variables, it may be a good idea to change it dynamically and dynamically understand what order would be better. And there are no hard formulas for such algorithms. Formulas that are hard for this proof system proved by Krajcik.
For pigeonhole principle, it's absolutely symmetric. It doesn't depend on the order of variables.
No, it's not symmetric because we have Pij, Pjk for different.
You mean holes?
Yes,
holes and pigeons.
Yes.
Mm-hmm. Okay.
I mean these variables. Okay, and if we also add reordering rule, no, I can say only about hard instances. We proved that there is a special kind of linear code such that the formula encodes that X is a coded word. In fact, this is a linear system, that this formula is hard for such kind of algorithms. This is interesting that SAT formulas that are also linear system are easy, but this formula is hard. But this is hard satisfiable formulas. For several years, I don't know. No, for me it was an important problem how to prove lower bound for unsatisfiable instances. But very recent, I think that I know it, and the idea that such kind of algorithm has the common weak point, that if we want to apply projection rule, we should download a lot of clauses. And if we have a lot of extra clauses that are actually do not needed to prove of unsatisfiability, but we also have to download them. And the hard and satisfiable instance is based on the following idea that either we have either we do not apply projection rule at all, and in this case we solve hard formulas for OBDD and proof system, or we have to download many unnecessary things, and in this branch we have to solve this hard satisfiable proof system in some sense. No, this is just a very rough idea. And we also prove that these algorithms do not simulate even tree-like resolution. That means that this approach is very different from resolution. Okay, and my last slide, take-home messages. First message, that using only conjunction rule is not a good idea. A weakening rule should be used if we want to solve. Weakening or projection rule should be used if you want to solve interesting instances. Sometimes reordering rule, order of variables is important, and dynamically reordering may be a good idea, and adding reordering rule breaks proof complexity barriers. OBDD approach, for my opinion, is underestimated and not enough studied. For example, the number of people studying CDCL approach and all other approaches in SAT solving is approximately the number of people in this audience without mask and with mask. Even if it is for my, maybe a right idea to have a mask. Okay, and further ideas. First of all, maybe it is good to combine OBDDs with other SAT solving heuristics. And for my personal idea is use not OBDD but non-deterministic OBDDs. This is a very this is extension of notion OBDD, but it has a very nice property, for example, that applying projection in this model does not increase the size. And also for non-deterministic OBDDs, there are other nice property that extension rule does not help to this proof, if proof system use non-deterministic OBDDs. But there is a problem because the property of minimizing it's not obvious. It is also easy to minimize the size for non-deterministic OBDDs, but computing operation is easy. Okay, that's all. Thank you for attention.
Well, Edward, yes.
You said reordering. So do you suggest to choose just any other order, maybe random order, or something carefully selected? So how to select an order?
I'm not an expert in this, but there are a lot of heuristics how to select an order.
Automatically, or some specific order for a set of?
I don't know details about it.
For example, even for pigeonhole principle, so we made some kind of prototype with projection conjunction system, and the problem is it's nearly impossible to find the right order of projection when. So I tried different automatic orders, and only when I read the paper, it worked. And so, for example, if I do my intuition to make these projections, it only maybe it become works for PHP 13 instead of PHP 12, and that's it. So the question maybe is how do you have some kind of intuition where to apply these projections automatically?
I'm not sure that this solving approach is the best one. I think that it is possible to devise a better approach. I present it only because it was studied. There are some papers about it. Maybe in this approach, it is not easy to efficiently solve pigeonhole, but some modification, I guess, possible.
Do you have an idea or intuition where BDD can be applied in SAT solvers? In which part? Maybe some combination of CDCL.
I think that yes, there's some combination that if we add some branching heuristics to this possibly, or maybe in CDCL, instead of learning clause, we can learn something more harder represented by OBDDs or something like this.
So use BDD as efficient data structures to store learned clause?
Probably yes. No, for me, it is important that it's finally the proof that will be produced by such algorithms is in more powerful proof system, and it is not obvious how to do it. And many pseudo-Boolean proof systems that use inequalities, they somehow can be simulated by resolution. It is maybe not very simple problem.
So, but as I understood, the last result said that BDD with projection and conjunction cannot simulate resolution. So it's not stronger nor weaker.
It is only about this SAT solving approach, not for proof system. They of course simulate and much more stronger.
Oh.
It's only for this particular approach.
Okay, thank you very much.